Hi, I'm Kuntan. I'm honored to have the opportunity to speak before all of you today. And my talk is about predicting acute kidney injury and resources utilization with the machine learning model based on the Meaning4 dataset. So first, why I want to focus on the acute kidney injury and I mean the AKI and also the resource utilization, the dialysis. Because AKI is a critical clinical complications marked by the sudden decline in kidney functions, and its prevalence extends to over 50% of the people in ICU, and leading to a mortality rate also up to 50%. And the AKI significantly impact on the healthcare resource, especially dialysis. Nowadays, many publications exist to try to solve the broad subject like the mortality rate, but the studies diving into the AKI, or especially for the dialysis, is still rare. And next, we'll move to whether we have the data. So the Meaning4 database is a public database. It's a rich source of electronic health records, which made it possible to thoroughly analyze complicated healthcare situations. And the Meaning4 database contains comprehensive time series measurements for the ICU, hospital, and emergency department, as well as complete clinical notes, which allow us to analyze and predict the disease from the multiple perspective. So we propose our approach and the solutions. So we first curate over 50 features and nearly 49,000 cases derived from Meaning4. And we propose our framework utilize 6 hours measurements to predict AKI and impending dialysis with a minimum 12 hours intervals before the clinical manifestation, meaning that there are at least 12 hours gap between the data we used, the last time point we used, and the clinical manifestation, which is important because nowadays some model try to predict the disease in the next 24 hours without a gap. Then it's high possibility that the disease will be diagnosed just after the last measurement, which means the measurements already involve the signals, and the healthcare team already observed the patients in poor health, which means the model is not that useful in that case. And then we examined with various models in both time series and clinical notes, and created a multimodal model for accurate predictions. So next, I will go into some details to how we do it. So in this slide, I will briefly describe the data processing. Firstly, for the time series data, we initially got nearly 51,000 patients with 66,000 admission records and also 73,000 ICU stays. In the first stage, for the cohort selection, we removed ICU transfers and also removed the multiple stays per admission, try to reduce the ambiguity of the outcome associated with the admission rather than ICU stays. And then we removed the patient age younger than 18 due to the difference between the adults and the children. And in stage 2, we first aggregate the measurement because we noticed that many item IDs which do the same measurement just because of the item ID has the early version and the later versions. So we do the aggregation first, and then we do the unit conversion and outlier remove because we found that many same measurements use the different units like the kilogram and pounds, and also some value of the measurements just out of the reasonable human ranges. In the third step, we do the hourly discretization, and then we do the imputation, like if in that hour there are multiple measurements, we take the nearest value. And if in that hour no measurements done, and then we take the value from the previous hours. And the last step, we also do the normalization. In the third stage, we select the data and label the patient. For example, we use the KDIGO criterion to label the patients whether they will be diagnosed as AKI or will not. Then from the diagnosed AKI patients, we, in addition, give the label whether the patient will need dialysis or not. So that's a time series data. And for the clinical notes data, each patient will have those subcategories. Because we are doing the predictions, so we cannot use any notes from the discharge. So basically, what we use is like history of the predental illness, past medical history, and also like the doctor impression or the measurement when the patient was admitted. So that's the notes data. So till now, we already have the time series data and the notes data. Then we go into the models. So these are the models we tested for the time series data. So here, the 3D dimension data is what we described from the last slide, which has like nearly 49,000 cases and over 50 features, and also 6 time points for each cases. No matter for the tree-based model, XGBoost, or the logistic regression, they need to flatten the data first, like from the 3D to 2D. And for the LSTM, we can directly input the time series data into the model. And then we get the results like this. We can see the LSTM always beats the other two, especially for the precision of the class 1, recall of the class 1, and also AUC on PRC. So by the way, the class 0 means the patient will not diagnosed with AKI, or the patient don't need the dialysis. And class 1 means the patients will be diagnosed and need the dialysis also. So in this case, I mean, the precision of the class 1 and the recall of the class 1 might be more important. And next, go to the model for the mimic4 nodes. So we use the BERT-based model, namely the PubMed BERT, which pre-trained from the scratch using the abstract from PubMed and the full articles from the PubMed Central. And also the clinical BERT, pre-trained from the BERT using the clinical notes, actually the mimic3 database directly. So actually those are pre-trained BERT or pre-trained model already. So what we need to do is fine-tune with our own data and for the specific tasks. I would like to give you some intuitions how it works for the predictions. For example, that's a already fine-tuned PubMed BERT model for the AKI prediction. And if we input the text like, he has noted dizziness, dyspnea on exertion, and chest pressure and so on, then we get an attention heat map. So this heat map is only the one head out of the 12 heads, and also the first layer out of the 12 layers. So from the attention head, we noticed those two words, the dyspnea and the chest pressure has the highest attention weight. That possible told us that may be useful for the AKI prediction because the model already fine-tuned based on the AKI prediction task. And we get some evidence from the Mayo Clinic. They show that the shortness of the breath and the chest pain could be the potential symptoms of the AKI, so that makes sense. And from the results, we see the PubMed BERT, like from the precision of class 1, recall the class 1, and especially for the AUC on PRC, has a better performance compared with the clinical BERT. And then we come up with the multimodal model, which combine the top performance model from both time series and the clinical notes by concatenate the embeddings. So for the time series model, we just get the embedding directly from the output of the LSTM. And for the BERT model, because the PubMed BERT has a limit for the input size, say 512 words, but the clinical notes are much longer than that. So we need to split the nodes into subsequences and feed into the model separately. Then we get each subsequences embedding, and then we take the mean, get the final embedding for the patients. Then we got the fusion, get the embedding concatenations. After that, we add the fully connected layer and the softmax to get the result. So from this result, we can see the multimodal model get much better results than the unimodal model, like the LSTM. For example, for the dialysis predictions, like for the recall class 1, we can detect 30% more patients who really need the dialysis, and nearly 15% more accurate for the dialysis prediction compared with the best unimodal model, and which lead to reduce serious and potential lethal complications and improve the patient's outcomes. And also, if we check the AUC of PRC, there are 25% more AUC of PRC indicates the model can significantly reduce the unnecessary the treatment or interventions, while ensuring critical cases are identified accurately. So going to the conclusion and the fusion directions. So we experiment with well-known models in time series and clinical notes domains, select the top performers in each area, and we integrate top-performing models to create a powerful multimodal model, enhancing the predictive accuracy for AKI and the impending dialysis by at least 12 hours before the clinical manifestation. And for clinical significance, our study emphasized the potential of advanced predictive modeling in aiding clinical decisions for AKI management and resource allocation. And predictive modeling can offer clinicians valuable insights for the timely intervention and personalized patient care, significantly improve the patient's health outcome. And for the future, we will conduct the further validation studies to ascertain the model's performance in diverse significant settings. And we will also collaborate with the clinicians to explore the practical implementations of our model in routine clinical practice. We will also do the model enhancement to further enhance the predictive accuracy. And that's for my talk, and I would like to acknowledge my co-authors for the great contribution for this work.
Thank you so much, Yukon. Questions?
Is this a proof of concept that you did, or is this an application in production?
Actually, it's an application, actually. So, I mean, we try to figure out how to solve the AKI and dialysis prediction problem, and we found out the data set and try to do it one step by step in this way.
So this is constantly monitoring patients coming in through the ICU. Okay.
Yeah.
Awesome. How painful was this to launch the application?
It's in clinical use right now, correct?
Not there yet. Not there yet, actually.
Oh, got it.
Yeah.
All right. Thank you.
Other questions?
You showed a lot of comparisons between the different methods.
Yeah.
Did you ever try combining them to see if maybe if together they would do better?
So what do you mean combining them?
Basically, for example, you did PubMed, BERT, and clinical BERT. Did you ever try?
To combine all of them together?
No, did you ever combine the results maybe to see if you could have a better predictor?
So I think that's what I try to create a multimodal model. So I didn't try to combine like the PubMed BERT and the clinical BERT together, but I try to combine the model from different input sources. Yeah.
Good questions. Any other questions? We got one right here. All the way in the back. You have a question?
Hello. Yeah. I would be more interested in what kind of statistical measures have you been used with the time series data?
So,
have you engineered any other features with the time series data? Have you created new features with that?
Yeah, actually we curate like more than 50 features for the time series data. Okay. So each feature will have 6 time points for each patient.
Because I've been working on a project which is almost similar to the kind of data, and we are making use of the quantiles approach.
What approach?
Quantiles.
Okay.
Yeah, 25th percentile and the data which is above 75th percentile. By any chance, have you made use of similar approach in your thing?
Actually, I'm not really familiar with your approach, but maybe we can discuss later.
Yep, sure.
Okay, one more question.
Thank you, Dr. Tan. I am interested in that table that you list the performance of combined model and individual models.
This one?
Yes. So I'm curious about why some of the columns we can see that from LSTM to multimodal model, the improvement is like about between 5 to 10%, but for error on the curve at the last column, the improvement was significant. Can you make some comment on it?
Yeah, because I think the problem is that for dialysis prediction, there is an imbalanced data problem. For dialysis patients, like there are only 10% of the total data. That's an imbalanced data set. For the ACAP prediction, it's much better.
Got it. Thank you.
Thank you, Yukon. We appreciate it.